In this lesson, we're going to continue to flesh out the concept of resonance. We're going to do a few examples, and we'll start with the one drawn here. So we'll say example 1. All right, and so if we look at this structure, we see that there are a set of lone pairs next to, adjacent to a double bond. So I'm just going to go ahead and start numbering this carbon 1 and that carbon 2, and then the oxygen 3. So I don't want to circle them just to give myself a little room and to be a little bit smaller with those numbers. So these are arbitrary numbers, but I'm starting with the electron density, which is the lone pair. And so what happens is the lone pair will drop down to form a bond between carbon 1 and carbon 2. Now carbon 2 already has a full octet. I'll write this down here. Carbon 2 has full octet. Something has to leave in order for that lone pair to drop down in the form of a double bond. Now, what leaves is this double bond goes onto the oxygen in the form of a lone pair. So two things happen. The first is a lone pair drops down to form double bond between carbon 1 and 2. Right, carbons 1 and 2, right? And the second thing that happens is the double bond becomes a lone pair. Okay, and so I'm going to draw the resonance arrow over and to the new structure, and it's going to look like this. All right, so let's recap this using a little bit of color. So here are the lone pairs. They drop down to form a double bond. So this is the double bond that was once a set of lone or a lone pair, right? So that dropped down, and then the bond that was in the double bond went up to become a lone pair, right? And so again, to recap, double bond becomes a lone pair, and then the lone pair, excuse me, I want to get it in blue, and let me erase this. Lone pair drops down to form a double bond between 1 and 2. And so we can see where everything ended up by the colors. The blue lone pairs on the left structure went down to become a double bond on the right, and then the red double bond that was on the carbonyl, that's the name of the functional group, but the double bond, the red, was between carbon and oxygen, ended up being a lone pair here on the second structure to the right? And so because this is resonance and both structures exist at the exact same time, we can also go the opposite direction. So these lone pairs can drop down, become that double bond again, and then this double bond can become a lone pair again. Right? And so they would go back and forth. Now remember, the resonance arrow is not about equilibrium. It's not strictly speaking going back and forth, right? What it is both of these structures at the same time. But we're showing the arrow pushing to show that that's how it would go back to the other structure, or that's how both exist at the exact same time. And so again, if I were to draw or explain what happened, we had a lone pair became a double bond, And then here we have a double bond became a lone pair. So the double bond becomes ultimately a lone pair. So that's our first example. I want to point out here with resonance, two things happen in pairs. I will say things move in pairs. So if we look back, two things happen. The double bond becomes a lone pair, and then the lone pair drop down to form the double bond between carbons 1 and 2. Or actually, this would happen first, and then the double bond would become a lone pair, right? But two things happen ultimately in that resonance structure, right? And so we're going to talk about what pairs of things essentially happen at the same time. They can change depending on what we have going on. So let's do another example. So we'll say example 2. And we will go ahead and give this as our example. Now, let's review. I'll go over here. The definition of resonance, or what things have to happen for us to have resonance. So we said three things. One, valid Lewis structures. Two, write it in blue. We have, actually I'll write it in green to stay faithful to the last lesson. We have the same connectivity of atoms, essentially the same backbone. And then number 3, is going to be different positions for multiple bonds and unshared electrons. Yeah, so same position for multiple bonds, different positions for multiple bonds and unshared electrons. So let's take a look at this. Here is the multiple bond, it's there, the double bond is there, but now what is there? So we have a different position for the double bond. Let's look at the lone pairs. Here, the unshared electrons are on the oxygen in this case, and they're on the carbon in that case. So again, rule number 3 is satisfied, and so this is checked. Let's take a look at the connectivity of the atoms, the backbone of everything. So we have all of the backbones the same. Carbon with connected to a carbon, the 1,2 bond, a carbon connection to oxygen, and a 2,3 bond. Yeah, on the left it has a double bond there, but on the right it's only a single bond. So essentially we only care about the backbone. And so if I were to go back and draw the resonance hybrid, remember step 1 is to look at what all is the same. And so I'll go ahead and draw the backbone. So there's the hydrogen, the carbon-oxygen bond, and the carbon-carbon bond. That is the same in both structures. That didn't change, right? And so now what changed is essentially the positions of the double bond. In the right structure, it was between carbons 1 and 2. And in the left structure, it's between carbons 2 and 3, right? And so in the left structure, we have the negative charge on carbon 1, so that will get a partial negative. And in the right structure, we have the negative charge on carbon number or oxygen number 3, so that will get a negative charge. And so this will be our resonance hybrid. To indicate that both of these structures are occurring at the exact same time. Again, it's not an equilibrium between the two. Both are existing at the exact same time. So I'm going to go ahead and work example 2 lower so I can get more space. So just copy it over from up here. I have a positive charge next to a double bond. And so what's going to happen here is convention is we always move electron density over. A positive charge is nothing more or less than the absence of a charge. The absence of something never moves. So we can't move a positive charge because there's nothing to move with a positive charge. It's the absence of charge. We have to start by moving anything with electron density. So a lone pair or a bond, which is essentially a lone pair shared across two atoms, is what moves. And so when this moves, we have the resonance structure. So let's number this. This is 1, 2. Actually, we'll start with 1, 2, 3. The double bond moved from between carbons 2 and 3 to between carbon 1 and 2. So let's go ahead and draw that. Now, the positive charge goes onto carbon 3, and we'll flesh that out here in a second. I'll erase this to make it look a little nicer. It's not much nicer, but it does the job. And so what happened here is a double bond moved from between carbons 2 and 3 to between carbon 1 and 2. So remember, we said things happen in pairs, and the second thing that happened in here, the positive charge moved from carbon 1 to carbon 3. Now, again, we don't have an arrow for a positive charge moving. It just moves because, again, the positive charge is just an indicator of absence of charge. So we don't draw anything over. Students will make that mistake again and again. If you're drawing an arrow moving, starting from a positive charge like this, or in that direction, or there, or anything coming out of a positive charge, you're wrong. You can't have anything out of a positive charge. Where arrows can only start from lone pairs and multiple bonds, right? And so this is our resonance structure, right? We can do the reverse, which is move the arrows down. So let's talk about the double bond here became this double bond, and then again it went back to that 2 to 3 carbon position. And then essentially the positive charge moves from carbon 1 to carbon 3. Now, let's go back a little bit and see why we couldn't move the arrow the opposite direction. Why not move the arrow there? I'll draw it in red to indicate it's incorrect. Why can't I move my arrow in between? Let's see here, better arrow. Why can't I move my arrow between there? The reason that is because I already have a full octet here and nothing can move. I can do that with a positive charge because I only had one hydrogen. There is essentially an absence of electron density that double bond can move into. Here there is no absence of electron density because there are already 2 hydrogens available there, right? And so the point of this is that we essentially can't move into that space because there is no absence of charge to move into. We can only move towards the positive charge, right? And so if we look at the steps on the right-hand side, a pair of things happen. Bond, double bond. moves or moved from carbon between carbons 1 and 2 to between carbons 2 and 3. And the second thing, remember I told you these things happen in pairs to get you used to moving around. And so if I were to just move the positive charge over, or excuse me, the double bond over and keep the positive charge where it was, that would be incorrect. So I have to move positive charge. So the positive charge moved from carbon 3 to carbon 1. Right? So a pair of things happened, and that was the pair. Now let's do another similar example. If I were to draw the resonance hybrid, actually, before we move on, what would that look like? So the hexane ring, essentially, the cyclohexane, excuse me, is going to be the backbone. And then if I look in one structure, I have a double bond there, and in the other structure, I have the double bond there. The positive charge is on 3 in one structure, so that gets a partial positive there, and on 1 in the other structure. So that would be my resonance hybrid for this molecule. It indicates that both of these exist at the exact same time. So I'm drawing all over the place here. Let's continue on to our next example, example number 3. And we're not going to do the resonance hybrid for this one. I want to move through this a little bit more quickly. And so in this case, rather than have a positive charge adjacent to the double bond, we're going to have a negative charge. And so we start by drawing from the lone pairs down, and that would kick the double bond out onto the carbon. So if I were to number this, 1, 2, 3, we would lone pair becomes double bond, and then the double bond becomes lone pair. Right, so we saw two things are happening at the exact same time, and we could draw a resonance arrow to show the new structure. That would be there, negative charge there. Pull this up, and then the double bond there. And these two would be resonance structures of each other. And again, I could do the same thing on this one. The lone pair drops into the double bond to form a lone pair there. Again, why didn't I move the arrow over the double bond over here or the lone pair over there? The reason I did not do that is because there are no essentially ways to do that, because there's a full octet on this atom right here. There's a full octet and a full octet. We can't move into something with a full octet. We could move down here, because as we move into something, even though 2 currently has a full octet, the lone pair can get kicked out and we no longer have the full octet, so it can accommodate for that double bond. And so the double bond becomes a lone pair on 3. So 1, 2, 3 over there. Remember, everything in resonance happens in pairs. 2 things are going on when we're pushing arrows or moving things about. Right? So in this case, the lone pair became a double bond, and then the double bond became a lone pair. Last example. Here, what we have is essentially, let me erase the ring. We have a lone pair adjacent to a positive charge. And so what we'll do is we always start the arrow from the lone pairs and we drop it down between the carbon and the oxygen. So if I give the oxygen designation of 1 and the carbon with the positive charge designation of 2, the lone pair becomes double bond between oxygen 1 and carbon 2. Okay, and then we said things happen in pair. The positive charge moves onto the oxygen. Again, we don't draw an arrow from the positive charge. Why? Because we can't draw an arrow from the absence of something. So now we have only one lone pair where there were two. I'll actually draw it a little bit differently so you guys can see. And I'll put colors on this lone pair that dropped and became that bond, right? So you guys can see the movement. And so this is the other resonance structure. If I have to draw the reverse and go backwards, I would draw from the lone pair, from the double bond going back onto a lone pair, and the positive charge, which I forgot to draw, should be here. Let me go ahead and draw it in a different color. Positive charge was here, and it was here. It moved, and then we go back and forth between these structures. Again, that's not technically correct because both these structures exist at the same time. But what we're showing is that the arrow pushing of the electrons is moving the electrons all around at the same time, and so we end up getting a structure that is actually both of those at the same time, which we show with the resonance hybrid structure. Now, let's go over an overarching understanding of what resonance is. So there are four possible situations for resonance to occur. So the first is a lone pair. I'll draw these in colors. Make this a little thicker. Adjacent to a multiple bond. Okay, the second one is when you have a positive charge adjacent to a multiple bond. When I say multiple bond, I mean double or triple bond. And then I'll go number 3 is going to be a lone pair. Oops. Adjacent to a positive charge, and I'll just say 1-2 relationship. Here we'll say it's across 1, 2, 3 atoms, and there it's across 1, 2, 3 atoms as well. Whereas number 3 only deals with being across two bonds. So then when we go to number 4, it's a radical adjacent to multiple bond. All right, now let's give an example of this. This would actually be very similar to the first example, but I'll go ahead and make it a separate example just to show you guys. So let's go over number 1. And so number 1 is going to be a lone pair adjacent to a multiple bond. And so that is this. Here is carbon 1, 2, and 3. The resonance occurs across 3 different atoms. Doesn't have to be carbons all the time, but they're different atoms. Okay, so that's example 1. Example 2 is a positive charge adjacent to a multiple bond. Example 3 would be a lone pair next to a positive charge in a 1-2 relationship. I can equally draw it like this, with a carbon there instead, negative charge. I can also do there. Any type of lone pair right next to a positive charge would be considered as the third type of resonance. And then lastly, we have a radical, I'm looking for a radical adjacent to a multiple bond. Now, what can we do with this? Let's go over these. Okay, we can drop, 2 things happening, drop that lone pair, right? We can draw the lone pairs in if we want, drop that lone pair between 1 and 2 to form a bond, which would kick the double bond out into becoming a lone pair on 3. Here, something different would happen. We have to start moving from electron density, which in this case is the double bond, and that would move over, and then the positive charge would essentially move as the second pair, or the second. There we go. So this would be, these would be resonance structures. Okay, and then I can even draw the resonance structure for the first case. And we're going to talk later on in what cases resonance don't occur, but these are the 4 situations. You want to look for these patterns repeating again and again. Now, they'll come in multiple different forms, but essentially, let me draw this one out this way. Essentially, these are the 4 possibilities of resonance occurring. And so these would be resonance structures. I'm not going to draw them for the other ones. And then we'll have something called homolytic cleavage, which we'll go over in a different lesson, but I just want to introduce it here today. This would be the 4th scenario of a resonance occurring, right? And so again, to boil these all down, and we can go back to these other examples. This was a positive charge, positive charge adjacent to a double bond. And then example 3 was a lone pair adjacent to a double bond. Example 4 was a lone pair adjacent to a positive charge. So 4 would be considered to a positive charge, 4 would be considered number 3. So we're going to put that in red because it's a lone pair adjacent to a positive charge. And then the example number 3 would be a lone pair adjacent to a multiple bond. So that would be 1. And then lastly, example 2 would be a positive charge adjacent to a multiple bond, right? So there are really only 4 different ways resonance can play out. Now, they could be on different atoms, they could be in completely different, dissimilar structures, and structures that look nothing alike at all. But again, the pattern is going to play out. So in this one, it's across 1, 2, 3, and then the only one where it just deals with 2 is essentially the case where you have a lone pair adjacent to a positive charge. So if we look at it, that would look like this right here. You have the lone pair. This is 1, that's 2. No other atoms are involved. Whereas the other ones, it's let's go to the blue on the left. It's 1, 2, 3. Hopefully this gives you a good overview of resonance, and we're going to need to practice this day in, day out, and get this skill down because it is crucial to the rest of the course.